Welcome to section 1b, where we're going to look at one-sided limits, continuity, and finally the intermediate value theorem.
The cool thing about the one-sided limits is I've already taught it to you a little bit. I've already worked it in previous lessons. So this is the limit as x approaches 3, and again you notice the superscript plus. That means from the right-handed side. Now what you want to do with a one-sided limit is you want to treat it like a normal limit first. If you can plug the 3 in directly and it works, you don't have to worry about the little plus. You just have an answer. Unfortunately, I think it's easy to see if you plug the 3 in, you're going to have a disaster. You're going to have 12 minus 12 over 18 minus 18. That's 0 over 0, which is indeterminate. Let's see if maybe at least we can factor. Up top in the numerator, I'll factor out a 4. In the denominator, I'll take out a 2. That would leave me with x squared minus 9, which I realize factors again into x plus 3, x minus 3. All right, the 4 and the 2 can cancel. The x minus 3's can completely cancel. And now we're just left with 2 over x plus 3, which is a lot safer looking. Now I can plug the 3 directly in. I don't even need the plus sign on it. It's going to be 2 over 6 either way. And of course we know that 2/6 is simplified to 1/3. So the moral of the story here on number 1 is just because you see a superscript, a little plus or a minus, you don't have to use it. If you can get away without needing it, you want to try that. Although that's not always going to be the case, as we will soon see. All right, number 2 is the limit as x approaches 5 from the left. Again, I want to just try a 5 directly in. If I did, I would have 10 plus 1, I'd have 11 over 0. Okay, 11 over 0, that sounds like infinity, but it could be negative infinity. I don't really know. Now I actually do have to legitimately go near 5 from the left, so I'm going to try in a 4.99. We'll see what happens there. Well, we have 2 times 4.99 plus 1. We have 4.99 minus 5. 2 times 4.99 is almost 2 times 5. It's almost 10, but it's actually 9.98. Plus 1, of course. And the denominator is going to be negative 0.01. All right, so you get that. If you were to move the decimal point over 2 places, you would just have a negative 1 on the bottom. Of course, the negative can slide around. I won't even need a fraction, but it's going to be negative 1,098. The answer here is going to be negative infinity. I can tell already. You're probably thinking, well, negative 1,098 is not negative infinity. I'm like, yeah, but that was if I used a 4.99. What if I went 4.999? What would happen is you'd have an extra 9 here and here. This would be 0.001. This would be 9.998. You get the idea. There's extra 9s, there's extra zeros. Now when you slot it over, you're going to end up with this, negative 10,998. And the closer you dare to get to 5 from the left, the more 9s you're going to have, the more zeros you're going to have. You will be approaching negative infinity. And also, too, it makes sense that x minus 5, since there's no factoring, is a vertical asymptote. And if there's a vertical asymptote at x equals 5, chances are as you're heading towards it from the left, you're going down to negative infinity. You'll never reach negative infinity, but that's why it's a limit. You don't have to get there. You just have to approach it. All right, we're approaching 9 from the left. We're approaching positive 9 from the left-hand side, so like 8.999. This is tough to tell. You can't try a 9 in because you're going to get 3 minus 3 over 9 minus 9, 0 over 0. But even if you try an 8.99 in, I'm not so sure we can rectify that because, all right, yeah, that's negative 0.01 like the last problem, but what's that? A little bit less than 3 ish minus 3. I mean, I don't really know what this is. I feel like I'm faking it because I am. All right, so that's no good. So we'll need a slightly different approach. There's a couple things you can do here. There's one real slick way, and then there's a more standard way. Most people don't notice the slick way, so I'm going to take you through the standard way. You need to multiply by the conjugate. Taking a page straight out of pre-calc, we're going to multiply by a giant green 1 in the form of radical x plus 3 over itself. This is going to make regular x plus 3 rad x minus 3 rad x. I'll blow those off because that just adds it to 0. Minus 9. Okay, so the numerator is x minus 9. I'm not going to bother foiling the denominator because I see canceling that will soon occur. So why waste my time foiling when I don't need to? So I won't. Now I can directly plug the 9 in. I don't even have to fumble around with the 8.999. I don't care if it's heading towards 9 from the left anymore. If I plug a 9 in, I get 3 plus 3 down there. So the answer is 1/6. And sure enough, this graph will head towards 1/6. They're 0.1666 repeating either way. But obviously heading from the left, we're going to approach 1/6. All right, there is an easier way that I alluded to, so let me get rid of my work and get 1/6 a different way. This is pretty savvy, but a lot of people don't realize x minus 9 can be factored. Wow. Yeah, it's radical x plus 3. I mean, who thinks to do this? Usually, about every class, there's one person that will be able to think like this on their own. Rad x minus 3, that works. And now these just straight away cancel. And you end up with the exact same thing that I got after doing all that foiling by the conjugate and stuff. Plugging the pure 9 in will give me 1 over 3 plus 3, 1/6. Just a lot cleaner. That's cool. Again, most people don't see that, though. But once you have seen it, maybe you think about it on your own. Who knows? All right, let's move ahead to number 4. Find the limit, if it exists. We want the limit as x approaches 2 of f of x, but f of x is a piecewise function. And at x equals 2, the rule has changed. You can see that the top part is linear, because that's just x to the first power. And the bottom isn't really linear. In fact, there's a vertical asymptote at 2/3. It's just different. All right, so let's plug a 2 into each one. Let's start up top and see what happens. 5 times 2, that's 10 minus 3, that's 7/4. Okay, 7 over 4. All right, let's try a 2 into the denominator of both places. 2 times 2 times 2, that's 8 minus 1. That's 7. This has a chance. 3 times 2, 6 minus 2, that is 4. They both head towards the point 2 comma 7/4. So yes, there is a limit, and the limit is 7/4. Some people like pictures better. Here's a quick illustration of what's going on. The red line is heading towards the point 2 comma 7/4. You can see it. The blue graph, I mean, goodness knows what that does. It's probably not that wiggly. But it also heads through the point 2 comma 7/4. The red has the equal to, so it actually connects. But even if it doesn't connect, there's still a limit there, and the limit still is 7/4. But this is colored in, just for the record. So it's also continuous. Obviously, the picture is not necessary. I had the answer long before I made any drawing. I just wanted to try to help people who were a little bit more visual. All right, that's 4 problems down. We have 13 total for day 1. But don't worry, they're quick hitters. All right, all 5 of these are just yes-no questions. Does f of negative 5 exist? In other words, if you go to negative 5 and you draw, this is not an asymptote, by the way, if you just draw a vertical line. Is anybody home along that line? Well, it's an open circle there. Nope. F of negative 5 does not exist. No. Does the limit of f of x as x approaches negative 5 from the right-hand side exist? In other words, as you approach that blue line along the function, Is there a limit? Yeah, there is. That's a yes. We're done with number 6. Since I like to go above and beyond, I'll even tell you I know what the limit is. It's 0. Even with an open circle, that's where you're heading towards. All right, number 7. Does the limit of f of x exist as x approaches negative 2? Let's move my blue line over at negative 2. As you approach that, does the limit exist? Well, if you head towards negative 2 from the left, you're approaching a height of 5, even though there's an open circle. As you approach negative 2 from the right, you're also heading towards a 5. So yes, there is a limit. The limit is 5, even though they didn't want that. People are like, what about this dot? I'm like, what about it? It's just there to mess with your confidence. It has nothing to do with number 7. It does have everything to do with number 8, though. Does f of negative 2 exist? Yes, it's positive 1 because of that red dot. If that red dot had not been there, the answer would be no. Finally, does the limit as x approaches 3 of f of x exist? So we want to take our action to positive 3. Again, this is not an asymptote, this is just a training wheels for myself. Along this line, is there a limit? No, we got some major jump discontinuity. Coming from the left, the limit as you head towards 3 would be 2. Coming from the right along this fish hook, it would be negative 3. But they're not the same limit, so therefore the overall limit, since there's no plus or minus there, dne does not exist. So no, there's no limit. Jump discontinuity. Number 10, does the limit as x approaches negative 2 of f of x equal f of negative 2? What? Sometimes that's easier to break down if you just sort of piece it together. F of negative 2, as we saw already, is right here, so that's 1. We've already solved this as well. What's the limit as you approach negative 2? Well, it's 5. All right, let's reread the question. Does 5 equal 1? Yeah, not in my world. All right, that was easy. So sometimes it just takes a little bit of deciphering or translating. All right, what's the limit as x approaches 3 from the left? We've already seen this. We saw that there was no limit as you approached x equals 3 overall, but if you approach x equals 3 from the left, there is a limit, and that limit is 2. If you approach 3 from the right, again, you're coming around this little J hook. Yeah, there's a limit. But because the left and right-handed limits don't match each other, an overall limit didn't exist on the prior slide. And finally, last but not least, x is approaching 7 from the left. We want that limit. X equals 7 is this end of the graph, if you will. You're approaching it from the left, which is the only way you can approach it. And sure enough, there's a limit. It's how high you are at that dot, which happens to be a height of 6. The existence of a limit. I told you guys earlier I would formalize the definition of a limit. Here it is. We've already seen this. This just simply says, hey, look, if you're coming from the left, you can barely see this, but it says the limit is x approaches c from the left, got the little negative. And somebody else is approaching c from the right. X approaches c and there's a little plus. If those two are both L, meaning that you come to the same place, the same height, then the overall limit of f of x as x approaches c is L. All right, so if you are at the point c comma L, so here's x equals c. We'll just say that this is the point CL. Here's L on the y-axis. All this simply is saying is if you head towards C comma L from the left, and somebody else heads towards L, C comma L from the right, then there is a limit, and the limit is L. Yeah, sure. Even if that's not, a filled-in circle. So basically what I've been teaching you now is formalized as a theorem. And finally, last but certainly not least, this is straight from pre-calc. In fact, I shamelessly took my old slide and just brought it into this lesson. We know that there are three types of discontinuity: point, jump, and infinite. Point discontinuity is when literally just a single point is missing. Points are like the size of a pinprick. The only reason we make circles is so people in the back row can see where we're at. Really, points don't even take up space in geometry, so a tiny point is missing. Some people think that this is jump discontinuity when I put a dot somewhere else. They think, oh, you're going along and you have to jump to get to this, and you jump back to the line. I'm like, no, it's still point. That doesn't count as jump. If this is your arm, and you're like the most valuable player on your athletic team, and you get a little bone spur, like a little piece, just a tiny little fragment comes out, you're not even going to notice that if it's the ninth inning and you're at bat, or fourth quarter in a football game, you're still going to play. However, if this is your arm and it snaps into two pieces, you're not playing it. We're taking you to Ahuja as fast as we can go, or Hillcrest, or wherever, maybe down to University Circle. Yeah, that's jump discontinuity. And finally, infinite discontinuity is the biggest jump ever. If jump discontinuity is you breaking your arm, infinite discontinuity is you broke your arm and you can't find the other part of it. It's so far away. Yeah, the last two are not going to have limits. Point discontinuity still allows limits to occur at that little point. Jump and infinite, no, a much bigger deal. Okay, so hopefully that helped. I put a little pre-calc spin on that just to bring the two classes together. That's it for day one. When we come back to day number 2, we're going to really get into continuity and types of discontinuity again. Still working them into calculus chapter 1. So I'll see you for the second half of this. Until we meet again, take care.